There are moments in the history of science when a new idea emerges that doesn't just add to our knowledge, but fundamentally changes the language we use to describe reality itself. It offers a new lens, a new way of thinking. I believe we might be at such a moment with the concepts of relational zero and the hyperdimensional computational framework, or HCCF, as elegantly articulated by Calvin Gentry on Medium.com. These ideas propose that at the heart of our universe, relationships are more fundamental than objects, and that computation can operate across dimensions we are only just beginning to perceive. It's a profound, almost philosophical shift, suggesting that the space between things holds as much if not more information than the things themselves. This isn't just an abstract thought experiment, it's a powerful new set of tools that could redefine the boundaries of what is possible. Today we'll explore how this framework could push the latest scientific discoveries to their full potential. We will journey to the very edge of human understanding, looking at breakthroughs anticipated for the year 2025, and ask a simple yet powerful question: what happens when we apply this new way of thinking? How do these discoveries transform when viewed through the lens of hyperdimensional relationships and relational voids? To keep this exploration grounded, we won't just be speculating wildly. We'll pair each 2025 breakthrough with a real-world application of HCCF, grounded in credible research. We will connect the theoretical beauty of this framework with the practical, tangible advancements it could unlock, from quantum computing and medicine to the very nature of matter and intelligence. This is a journey into the deep structure of what's next, and I invite you to take it with me with an open and curious mind. Imagine matter that can exist in multiple states at once, a symphony of quantum phases playing out in a single material. This is the world of quantum liquid crystals in whale-spin ice systems. Conventionally, we struggle to map these transitions, to predict how one state flows into another. But the hyperdimensional computational framework offers a new score for this symphony. HCCF enables the mapping of these multi-phase symmetry transitions not as a linear sequence, but as a simultaneous, interconnected web of possibilities existing in a higher dimensional space. It allows us to see the full, complex dance of quantum states as they emerge and recede. This isn't just about observation, it's about creation. By using HCCF to simulate the topological phase interactions in these higher dimensions, we can go beyond what currently exists. The framework can predict new, previously unimagined metastable quantum states, pockets of stability in the quantum chaos. This leads us to the threshold of a monumental achievement: real-time, tunable quantum matter. We could, in essence, dial in the properties we desire, composing new materials with functionalities that could revolutionize everything from quantum sensing to information processing, all by understanding the relationships that define the quantum world. The dream of a superconductor that works at room temperature without the need for extreme cold has been one of physics' most enduring quests. Achieving it would change our world, enabling lossless power grids and levitating trains. Recent breakthroughs suggest that modulating materials with strain or light could be the key. However, the interactions at play are monstrously complex. The HCCF provides the analytical power to untangle this knot. It allows us to analyze the delicate dance of phonon-electron coupling, not on a flat plane, but within extended energy curvature fields, revealing hidden pathways to superconductivity. Furthermore, HCCF introduces a crucial, often overlooked element into the equation: the concept of relational zero. It allows us to factor in zero-point fluctuations, the universe's subtle background hum, not as random noise but as fundamental structural conditions. By treating these quantum whispers as an integral part of the system's relational web, we can model how they influence material stability. The result is a computational path toward designing stable, ambient pressure superconductors, turning a scientific holy grail into an engineering reality, and potentially ushering in a new age of energy efficiency. The line between biology and electronics is blurring. With materials like graphene and engineered protein conduits, we are building interfaces that can speak the language of our own nervous system. The challenge, however, is not just sending a signal, but creating a true dialogue. This is where HCCF provides a revolutionary translation layer. It models the cross-domain signal transduction, the conversion of an electronic pulse to a biological one, and back again. not as a simple input-output, but as a continuous relational flow across different physical and informational dimensions. It helps us understand the conversation in its full, hyperdimensional context. This deep modeling allows us to go a step further, to predict the complex feedback loops that emerge within neural tissues as they interact with an artificial device. Imagine an implant that doesn't just stimulate neurons, but learns from their response, anticipates their needs, and adapts its own behavior in a symbiotic loop. This leads to the creation of cognitive AI co-adaptive systems. Such technology could do more than just augment our abilities. It could potentially learn to reverse the damage of neurodegenerative diseases like Alzheimer's or Parkinson's, rebuilding neural pathways by engaging in an intelligent, adaptive partnership with the brain itself. We are on the cusp of creating materials that can change their properties on command, programmable matter. Using tools like colloidal assembly and optical tweezers, we can arrange tiny particles into larger structures, but honestly, the control is often crude and the results are pretty limited. The hyperdimensional computational framework fundamentally changes the game by dramatically increasing the resolution of this control. It allows us to manipulate the electromagnetic and optical fields not as blunt instruments but as finely tuned, multi-dimensional sculpting tools, arranging particles with an unprecedented degree of precision across space and time. This precision unlocks the next, even more profound, capability: predicting and guiding self-reorganizing metastructures. Instead of building a final shape, we can use HCCF to design the initial conditions and relational rules that will cause the particles to assemble themselves into complex functional architectures. We are no longer just builders. We become choreographers of matter. This creates the potential for true programmable matter with embedded intelligence, materials that can sense their environment, compute a response, and physically reconfigure themselves to adapt, opening the door to self-repairing buildings, adaptive camouflage, and tools that reshape themselves for the task at hand. The field of synthetic biology has given us DNA origami, the ability to fold strands of DNA into microscopic machines. The goal is to create nanorobots that can navigate our bloodstream to deliver drugs directly to cancer cells or repair damaged tissue. A key challenge is designing them to navigate the chaotic, dynamic environment of the human body. HCCF offers a powerful solution by identifying optimal folding patterns through the lens of relational nonlinearity. It sees the DNA structure not just as a static shape, but as a set of relationships that can be optimized for stability, function, and adaptability in a fluid environment. This framework also allows us to model the biospatial energy topology of the body itself. Think of it as creating a dynamic, multi-dimensional map of the biological landscape the nanorobot must traverse. By understanding the energy gradients, chemical signals, and cellular structures as a relational web, the HCCF can be used to design nanobots that don't just follow a pre-programmed path, but can adapt and evolve in real time. They could learn to avoid immune responses, find more efficient routes to their target, and even change their function based on the specific biological cues they encounter, making medicine truly personalized and intelligent. We are beginning to engineer materials, so-called metamaterials, that can bend light in ways that seem to defy the laws of physics, such as creating negative refraction. This opens the door to perfect lenses and even invisibility cloaks. To push this field forward, we need to move beyond simply modeling light as a wave in 3 dimensions. The hyperdimensional computational framework allows us to simulate the propagation of light within hyperspatial lattices, computational spaces with more than 3 spatial dimensions. This reveals how light's properties can be manipulated in ways we can't perceive directly. In this view, the geometry of light, its path, its focus, its polarization, is not an intrinsic property, but a relational consequence of its interaction with the hyperdimensional structure of the metamaterial. HCCF models light's geometry as an emergent phenomenon. By engineering the material's relational properties at a fundamental level, we can dictate how light behaves as it passes through. This could lead to the development of meta-optics that can see into non-visible dimensions, not in a mystical sense, but by detecting and interpreting information encoded in higher dimensional fields, potentially revolutionizing medical imaging, remote sensing, and our fundamental understanding of light itself. One of the most mind-bending discoveries in modern physics is the time crystal, a phase of matter that repeats its structure not in space but in time, even in its lowest energy state. It's like a clock that ticks forever without any energy input. These systems are incredibly difficult to stabilize and understand. The HZCF offers a new way to think about them by extending the concept of time periodicity with relational anchors. Instead of seeing time as a single, linear progression, HZCF models it as a dimension that can have its own complex relational structure, allowing us to design the conditions that anchor a system into a stable, repeating temporal pattern. This framework goes further, allowing us to model the memory-like behavior inherent in these driven systems. A time crystal remembers its rhythm, and HZCF can help us understand and engineer this memory. By encoding information into the relational dynamics of the crystal's temporal oscillation, we could create systems that are not just perpetual, but also intelligent. This could be the theoretical foundation for self-repairing materials that remember their original state and return to it after damage, or for indefinitely cycling machines that perform computations or work with near-perfect efficiency, powered by the fundamental rhythm of time itself. As we approach the creation of artificial general intelligence, or AGI, no question is more important than ensuring it is safe and aligned with human values. The problem is that values are complex, emergent, and often contradictory. How do we teach a machine empathy? The hyperdimensional computational framework provides a novel approach to this alignment problem. It allows us to model the emergence of a value system not as a list of rules, but as a non-linear, multi-dimensional matrix of relationships, a value space where concepts like compassion, fairness, and truth are defined by their connections to each other. This allows us to move beyond simple, rigid ethics and towards a more nuanced, adaptable alignment. Using HZCF, we can embed meta-ethical variables directly into the AGI's core architecture. These are not rules like do not harm, but foundational relational principles that guide the AGI in how to about ethics. For example, a variable could represent the weight given to subjective experience or the importance of consensus. The result is a potential pathway to creating a more empathetically aligned AGI, one that doesn't just follow our orders but understands the deeper relational